Good morning. Today's lecture is on satellite based navigation and applications. Satellite navigation is a system that uses satellites to provide autonomous geospatial positioning. The first ever created such system was called Navistar Global Positioning System, which was prepared by United States Department of Defense. They have decided to establish, develop, test, acquire and deploy a spaceborne global positioning system resulting in the Navistar GPS. Navistar GPS stands for Navigation Satellite Timing and Ranging Global Positioning System. It is an all-weather space-based navigation system developed by US to satisfy the requirements of its military forces to accurately determine their position, velocity and time in a common reference frame anywhere on or near the earth on a continuous basis. It uses global coordinate system where the center of the earth is considered as the origin. The general characteristics of Navistar GPS are that it is accurate navigation to an order of about 10 to 20 meters. It has a worldwide coverage. It has 24-hour access and works on a common coordinate system. It has almost replaced all the earlier navigation systems as it is primarily independent of line of sight. So GPS has proved one step ahead of the other techniques, older techniques. Now it is accessible to civilians as well as defense. The first GPS satellite was launched on February 22nd, 1978. Along with the GPS generated by United States, GLONASS was developed by Russia. So when we are using multiple satellites together, we call that system as a global navigation satellite systems. So ICAO has defined global navigation satellite systems which is like this: a worldwide position and time determination system that includes one or more satellite constellations such as Navistar GPS of US and GLONASS of Russia, along with aircraft receivers and system integrity monitoring augmented as necessary to support the required navigation performance for the intended operation. So primarily the satellite constellations which are independent, like the Navistar GPS of US or the GLONASS of Russia, when they are being generated or utilized independently, they are known by their name as Navistar GPS or GLONASS. But when a receiver use both of them together, we call that as global navigation satellite system, and it can be integrated with the other receivers on air, sea or land as well. So GNSS is a super term as compared to the GPS or GLONASS, which encompass all similar systems. So USA has developed GPS, Russians has developed GLONASS, European Union is developing Galileo, Japan has developed QZSS, India has developed our own regional system known as Indian Regional Navigation Satellite System. China has developed BEDO, phase 1 has completed and phase 2 is in progress for China, and Australia has also developed augmentation systems. These systems can be understood in three segments. So for example, we are taking here the case of the Navistar GPS. So the first segment is the space segment, second is the control segment, and the third is the user segment. So under the space segment, various kind of blocks has been launched. These blocks are like first generation GPS satellites, second generation GPS satellites. So in case of GPS, the terminology used is the block. So block 1 satellites were launched between 1978 to 1985, under which 11 satellites were launched. They have completed their life. Then the second block were launched between 1989 to 1997. Then Block 2R was launched and Block 2F. So these are basically improvised, less weight and more efficient systems which have improvised over time because of the development in the electronics. Block 3 is going to start from the 2017. So these blocks are basically renamed from time to time based on the developments in the technology used in the generation or building up of the satellite. The Navistar GPS constellation was made operational in 1993 and it was used with limited purpose, so we call it as an initial operational capability. Then final full operational capability was called as FOC and it was declared in 1995. The overall initial cost was around $12 billion. Nowadays the launches which are going on, they are of an order of $5 billion. The annual operational cost is over $400 million. Segments, as I have told, the first is the satellite segment, which are in the space in the form of the GPS satellites moving in their respective orbits. Then we form the user segment. We are using the receivers, so all the users are basically the users segment. And then the control is the monitoring and control stations, which basically look after the GPS satellites which are in the orbit. In case of Navistar, we will call them the monitoring and control stations of Navistar. In case of GLONASS, they will be the monitoring and control stations for the GLONASS, and similar for the INSS satellites. For Navistar GPS, the prime space segment contractor was Rockwell International. Then it has gone to Boeing and then Lockheed Martin, and again it is with the Boeing. So these are the contractors who are making the satellite buses and the satellite systems used for the GPS purpose. GPS is working on the common coordinate system known as WGS-84, and it has the command from the US Air Force based in the Colorado Springs. So GPS segment can be further simplified as 6 orbits in which we are launching minimum 4 satellites, and these orbits are at an angle of 55 degree to the equator and separated by 60 degree along the longitude. So the entire longitude of 360 degree has been divided into 6 parts, and at every 60 degree we have an orbit with 4 GPS minimum in that. So it makes 6 orbit into 4 satellites per orbit. So minimum 24 orbits we are keeping, whereas the minimum mathematical requirement to cover the entire globe was 21. So we have 3 spares all the time. Over the time, the number of applications developed on GPS has increased tremendously. So actually, as a backup plan, more and more number of satellites have been kept, and at a time nowadays we are having 32 satellites at a time in the orbit. So we have around 8 or 10 spare satellites at a time. The control segment locations are at Colorado Springs, Hawaiian Islands, Ascension Islands, Diego Garcia in Indian Ocean, and Kwajalein Island. So these 5 were the initial control and monitoring stations utilized. Over time, more number has developed at various locations, but these were the initial 5 stations with master control facility or the main station at Colorado Springs, which can be called as the headquarter. Master control station has the job to collect all the data which monitoring stations collect from the satellites. The monitoring stations are responsible for measuring pseudo range. The orbital tracking network is used to determine the broadcast ephemeris and satellite clock modeling. Ground control stations with antennas such as S-band link, it is used for uplinking the information to the satellites in their coverage areas, and they take care of the routine maintenance also. So primarily the data is collected by the monitoring stations and all of it is submitted to the master control stations for further corrections. After corrections, the broadcast ephemeris is called as the precise ephemeris, which takes around 2 weeks of time, 10 to 14 days, and it is uploaded onto the internet for further processing of the data. So till now we have talked about the GPS segment and the ground segment, that is the control segment. Now it is the user segment. So user segment comprises of all the people or the agencies who uses the system. So this is the most visible segment. Almost everybody is using nowadays GPS in some one or another form. Most one is the like the car navigation system, which is in great use nowadays. Otherwise the defense agencies like merchant, navy, coast guard systems, surveyors, hikers, mountain climbers, all these are using GPS nowadays. Why we are using GPS, why it has become so relevant for the time and so important? Because it is weather independent. Whether it is raining or it is foggy or snow, all the time we are able to get the GPS signals. It do not require line of sight. It gives us the geodetic accuracy. It can be operated day and night. It is very fast and require very less manpower. It has economical advantages. Nowadays we are getting GPS systems ranging from 5,000 rupees to lakhs of rupees depending upon the accuracy requirements and the complexity of the systems. But it has come down to an cost of about 5,000 rupees. It works on the common coordinate systems. There are a large amount of applications built up and it is competitively priced. The working of the GPS can be explained in 5 easy steps, which can be more clear with the figure. So basically what is happening, that the receiver is receiving the signal from the satellite. When the satellite emanates the signal, the time t1 is recorded, at which the signal starts from the satellite, and the time is recorded at the receiver end when the signals are received by the receiver. So we have two times, t1 at which the signal starts from the satellite and t2 at the receiver end. By subtracting t2 and t1 we get delta t. So this delta t represent the time which signal has taken from the satellite to reach the receiver, and this delta t, when we multiply with speed of light, it gives us the range or the pseudo range, that is the distance between the satellite and the receiver. This range puts the user on a sphere around the satellite, and several such spheres when intersect, they give us the user position, that we call as the triangulation, which will also be explained. So there was a phenomena called selective availability, under which the US agency can deteriorate the signal, and in that case we can get an accuracy of the order of 10 to 100 meter, which was the case before May 2000. But this feature called selective availability has been removed now. It has been put off for the time being, and currently the accuracy which we are getting from the receiver is of the order of 10 to 20 meters. This is the standalone accuracy which can be improvised using different methods. So here what is happening, that the satellites are acting as control stations. They are the orbiting control stations. It is a dynamic system, and these control stations are being used to calculate the position of the receiver on the earth. In that, time is playing a very important role, and any error in the time deviates us from the correct position. So to understand that, we can see here, if we have an error of 1/10 second, we will have 30,000 kilometer error in the positioning. If we have a microsecond of an error, then also we have 300 meter of an error in position. So that means we require a very good clock of the order of 1 in 10 to the power 13 or 10 to the power 14, so that we can achieve an accuracy of few centimeters or millimeters after processing. The triangulation process is explained here in this figure, wherein we see that if we have this as the satellite, and after calculating the pseudo range by subtraction of T2 and T1, multiplication with the velocity of light, user is somewhere on this entire sphere. So there is a large uncertainty, but when we get from two satellites, when we get the signal from two satellites, we can intersect the two spheres, and it will narrow down our uncertainty to this particular circle which is generated after intersection of the two spheres. Once we get position from the third satellite also, it will generate two intersection points among three spheres over which GPS should be there. So finally we have landed up with 2 points over which the GPS is possible to be there. GPS receiver is possible to be there. So one of this is a vague solution and another is the real solution. So like this, by using signal from 3 satellites, we can get the position of the GPS receiver. So as already I have told that timing is very important here, but there is a catch here. What is happening that on the satellites we have atomic oscillators, we have atomic clocks such as rubidium clock or cesium clock, which are very highly precise and highly accurate, whereas on the receiver we have a cheaper instead of atomic clock we have a quartz clock. So there is a difference in the precision of the clock being used at the satellite and being used at the receiver end. So there is a precisional difference between the time calculated at the receiver end and the time calculated at the satellite clock. So this generates a parameter called clock bias. So what happens, we have three unknowns, that is x, y, z. X is the longitude, y is the latitude, and z is the elevation above the datum, which is a WGS84 in this case. So another parameter comes into picture because of the difference in clocks, that is called the clock bias, that is represented by the B. So now we have got 4 unknowns instead of 3. So as we have seen in the previous slide that we require 3 satellites which are being used to create equations to solve these 3 parameters. Now the number of parameters has increased to 4. One additional parameter has come in the form of clock bias represented by B. So instead of 3 we have to create 4 equations like this. So we have pseudo range, that is the distance between the satellite and the receiver, given by this equation, wherein we are taking care of the clock bias also. So instead of 3 we require 4 equations now, and these equations are solved dynamically in the GPS receiver. That is why when you are operating the GPS receiver, you might have seen that the solution is continuously varying, the latitude, longitude and height. You will see continuous variation in the solution. So now we have seen the 3 segments of GPS. We have understood the working of the GPS in form of 5 easy steps, and we have seen the triangulation also, how we are zeroing down onto the receiver location using 4 satellite signals. If there would have been similar clocks onto the receiver, clock bias could have been avoided, but that practically that is difficult. So we have one more unknown in the form of clock bias. So we have 4 unknowns, and thereby we are using 4 signals. So the answer to the question that how many signals or the satellites are required for getting position is now 4 instead of 3. 3 would have been the case of ideal situation, and 4 is the real answer because of the clock bias. Next comes is the GPS signal structure. So this slide explains the signal structure of GPS. In a simple form, we are using here two carrier waves L1 and L2 here, which are basically the carrier waves, and their job is to carry the codes, the codes acquisition code which we are using for civilian application, and the precise code which we are using for the defense applications from the satellite to the receiver. So L1 and L2 are known as carrier waves, which carry the codes acquisition code and P code from the satellite to the receiver. The wavelength of L1 is 19 centimeter, wavelength of L2 is 23 centimeter, and similarly they have various frequencies. With the new systems which are coming into picture, we are getting additional L5 frequency. It is already there with around 12 satellites. L2C is under testing, and L1C for civilian applications will start from third series. So currently we are using only two carrier waves primarily, but third L5 has also been added. So three are already available to us. In the coming days more will be added into the network, such as L2C and L1C also. There is L3 also, which is used for nuclear detection, but this is not available to us. Coming to the surveying techniques, we primarily use four surveying techniques using GPS. One is for differential GPS purpose, wherein we are using more than one GPS at a time. This method is known as static GPS survey, which is primarily used for calculating the control points and creating large national networks over the landscape for the bigger projects. This is used when we are having long baselines more than 20 kilometers. When the baselines are long, what happens? The survey time also increases. So here we have a point called as base point, which is at a known location. That system works continuously, whereas the rover systems works on the control point, and the duration of operation at the control point is increasing if the baseline is increasing. So there is a relation between the longer baseline and the duration for which we are going to operate it. The reason behind that is that we need to have common satellites between the rover and the base. So if the distance or the baseline between the rover and the base is more, we have to wait for the four common satellite systems. It takes time. Whereas if the baselines are short, let us say of the order of 5 to 10 kilometers or less than 20 kilometers, we can have rapid static surveys wherein the rover will operate for lesser time, such as 20-30 minutes. So that will be sufficient. So we will have short occupation times resulting in high production, but under the rapid static we have to limit the baseline. So this will work when our study areas are less, but whenever we are working over large areas or large cities such as 1300, 1500 square kilometer areas of bigger cities, we have to use differential GPS systems which have dual frequency and which have geodetic receivers. So rapid static and static are similar in nature. The main difference is in the terms of the length of the baseline. Then there is a third category called stop and go method of GPS survey. This is for primarily the utility mapping. For example, suppose we have to map all the electric poles in the city. So we need not to go for a very high accurate system. What we can do is we can have a handheld GPS, because we have to take thousands of observations and there are thousands and thousands of poles. So there what we can do, we can have a stoppage at every pole, take a reading and move to the next pole. So this is called stop and go method wherein we are taking a single observation, maybe two observation at a point and moving ahead. Similarly, like for suppose we have a project called like tree outside forest. If we have to map the trees outside forest area in some our study area, then also we can have a observation at a tree and move to the next tree. So basically this is primarily for utility mapping. So stop and go works like that. Whereas the fourth application, which is another interesting application, is kinematic application, wherein we are interested in creating the complete trajectory. So like this method is being used for mapping of like the movement of the aircraft from one place to another place, like tracking the missiles or tracking a vehicle. So in that we use kinematic method. Now at a moment, what kind of accuracy we are getting? So that depends upon the satellite geometry at that point of time. So similar to root mean square error, we have a term called positional dilution of precision, which is a simplified method for any naive user who need not to go into the complexity of the calculations. So a function called dilution of precision or the positional dilution of precision has been developed for GPS. It is a unitless number and it directly tells us about the quality of the signal, and which can be understood as the signal is of very good quality if the number lies between 1 to 3 DOP value. If the value lies between 4 to 5 for dilution of precision, that is DOP, it is considered good. If it is 6, it is considered fair, and it is considered as not reliable or susceptible if the value of dilution of precision is more than 6. So when it is more than 6, we should not go for the observation. If the satellites are inclined towards one side, we consider it poor. If they are having a good spread all around the receiver, then we consider it as a good dilution of precision. There are applications wherein the user is interested in latitude, longitude, height and time, all the four. So if we take care of all the four, the dilution of precision is called geometric dilution of precision. If someone is or some user is interested in latitude, longitude and height, we call it positional dilution of precision. If the user is interested in the accuracy of latitude and longitude only, we call it horizontal dilution of precision. If someone is interested in height only, we call it a vertical dilution of precision. Now how this is defined as good or bad can be seen here. If we have a good spread of satellite above the receiver, so receiver in this figure is considered as at the center. So if there is a good spread of the satellites, they generate less uncertainty, as can be seen here by the triangulation which was talked earlier, wherein we are intersecting the various spheres which we are making around the satellite using the delta t multiplied by c. Whereas if the satellite geometry is skewed, that is there may be large number of satellites but they are skewed to one side of the receiver. Receiver in this figure, again I will repeat, it is considered at the center of this circle. So if the geometry or the position of the satellite is skewed to one side, it creates large uncertainty, and so we consider it as a poor satellite geometry. So now we have talked about the triangulation method, how GPS works, what are the various segments, what are the carrier frequencies, the two codes, course acquisition code and the precise code for the defense. Now we will see that what are the kind of GPS receivers available in the market. So the GPS receivers available in the market are distinguished in terms of like single frequency. If they are only receiving L1 frequency, then we call them single frequency receivers. They are relatively cheaper receivers, and they can give us an accuracy of the order of 1 centimeter to 5 millimeter. The latest one are giving an accuracy of 5 millimeter plus 1 ppm. They are working on only L1 frequency. They are used for network densification. The limitation here is that we are using them for study areas ranging to an order of 15 kilometer by in terms of the baseline between the rover and the base. So whenever we have a small study area, we can use single frequency receivers, but whenever we are working over large areas where we have baselines of 20 kilometers, 50 kilometers or 100 or 200 kilometers, there we are using dual frequency receivers. So we are basically using dual frequency receivers when we are working over very large areas, full cities or state or countrywide. So there we are using dual frequency receiver. They are high-end systems, and they are able to give accuracies of the order of 3 millimeter plus 1 ppm. See here, what we can see that single frequency receivers are also able to give 5 millimeter plus 1 ppm accuracy. So there is not much difference between the accuracy, but the main difference is that when we are using single frequency receiver, the area we have to limit. There is a limitation that we can work over baselines of around 15 to 20 kilometer only. That is the primary difference between the single and dual frequency receivers. Besides that, single frequency receiver is getting L1 only, whereas dual frequency receivers are getting L1 and L2 both. But dual frequency receivers, a set of receiver like one base and one rover, we are getting in something like 15 to 20 lakh rupees, whereas single frequency receivers we can get in less than 5 lakh rupees. So depending upon the project cost and the study area, we can choose single frequency receivers or the dual frequency receivers. But we would like to suggest the use of dual frequency receiver for high-end applications covering larger areas and important projects. When we are using the receiver as a standalone device, then we are getting an accuracy of the order of 10 to 30 meters nowadays, wherein different type of errors contribute to the overall error. So we have user range errors, which consist of system errors and atmospheric errors. System errors comprises of ephemeris data and the satellite clock. Ephemeris data primarily means the coordinates of the satellite at a moment in an orbit, whereas atmospheric errors comprises of the ionospheric and tropospheric errors, which comes into picture when the signal travels from the satellite to the receiver passing through the atmosphere. Then there are user equipment errors also, which basically comprises of receiver noise and the multipath error. In an easy way, we can understand positional derivation of precision of 2 means that in the worst case, a 1 meter of user range error will result in 2 meter positional error. So the user range error, which is comprising of ephemeris data and satellite clocks, if it is of 1 meter, then the total error in position may be of 2 meter. So this is a thumb rule kind of thing. So that is one way to interpret the dilation of precision value. Now in the second case, if we are using more than one system, we are using a differential GPS system, then the satellite clock errors and orbital errors can be removed. So they can be brought down to 0 from 1.5 and from 2.5 respectively. The ionospheric error can also be removed. Tropospheric errors can also be removed to an order of 40 to 20 centimeter respectively, whereas the receiver noise cannot be corrected by the differential method also. Multipath also cannot be removed, but multipath can be reduced by using some other appropriate antennas. So one of such antenna is called choke ring antenna. So this is a specially designed antenna which can control the multipath error. Now we will see what are the systems available right now. So we have global positioning system, that is the Navistar GPS system belonging to US, and with various features which are listed in this table. It is using 6 orbits and there are 30 satellites in them, whereas the GLONASS, which belongs to Russia, it is using 3 orbits with 24 satellites. Galileo, which is incomplete currently, it is planned to have 30 satellites in 3 orbits. There are some other statistical differences between these 3 satellite systems which are shown in this table. Now coming to Indian position. So you are aware that it is a matter of pleasure that the Indian agency, the Indian Space Research Organization, has been successful to complete the Indian regional navigation satellites. So there are 7 satellites now working round the clock, giving position to the IRNSS receivers within India and to an extent of 1500 kilometers from the Indian borders. So the IRNSS has been completed. Currently we have 7 satellites in it, and we are going to add 4 more satellites, spare satellites, to the system, so that we will have 11 satellites in our IRNSS constellation also. As far as space based navigation systems are there, we are already using Gagan for the taking off and landing of aircrafts. Gagan is a project between Airport Authority of India and ISRO. A large number of GPS applications are already in use, and various departments, government departments, are already using it along with the International Space Station, which belongs to the international community, and various spacecrafts. So we can see here National Remote Sensing Center, Hyderabad, Survey of India, Military Survey, National Hydrographic Office, various land record departments, oil and energy departments, power departments, defense agencies, scientific institutions in India, mining and geology departments, various consultancy firms, various engineering and infrastructure firms, and private companies. All of them are using GPS nowadays. So it is a high pleasure to talk about it here that the Indian system, the Indian Regional Navigation Satellite System, is complete, and all these agencies can and will be able to use our own system in the coming days. Many of these are already using with the receivers given by Space Application Center currently. So at IRS also we are using the IRNSS receivers, and we have found that it is giving us much higher accuracy than what we were supposed to deliver. We are getting much better accuracies. So we have various applications which can be seen from the point of various ministries. So we have precision agriculture, where we can have precision farming. It can be utilized by the agriculture ministry. Personal navigation has come out to be as a very useful technology for a general user. So in the car we can have car navigation, and anybody will be able to use it very simply. We are using it for the aviation, we are using for the recreation purpose in the trucks and shippings, railways, fishing and boats. So the 4 methods which we have talked about, the rapid static method, the static method, the stop and go, and the kinematic method. So all these 4 methods, as per the requirement, can be used by different agencies. There is a table which describes the kind of application we require, like geodetic infrastructure, fault monitoring, construction surveys, engineering surveys, geodynamics. These are high-end applications used for earth moving, road grading, that is the giving the slope. So these require high accuracies of the order of better than 20 centimeter. So they have to choose accordingly the kind of receiver they want to use. So as I can tell here, for this kind of applications we will have to use dual frequency receivers, high and geodetic receivers, whereas for resource mapping, GIS database, utility mapping, highway surveys, legal surveys, there is a little more margin with us, and we can use one grade lesser GPS receivers or processing methods which are able to give us an accuracy of the order of 20 centimeter to 1.5 meter. Similarly, for other applications like navigation, we can tolerate from 1 to 5 meter of an error depending upon case to case basically. So we can have a cheaper receiver for this kind of application. For reconnaissance survey, need not to specify, we can use lowest receiver also costing around 5000 rupees also, which can easily give us an accuracy of the order of 10 to 20 meters. If the DOP is good, it can give better than 10 meter also, it can give at a moment 5 meter to 1 meter also. That depends upon sometime on the satellite geometry. So in a very good favorable condition, from a very cheaper receiver also we can get very good results. So what we have to understand here is that primarily the accuracy requirement depends upon the application what we want to do, and accordingly we can use the GPS, we can choose the GPS receiver and do our work. So basically the reason to choose a GPS receiver is primarily the application. So depending upon the application we can choose a receiver and do our work. In the conclusion, I would like to say that we should use this technology and never lose our position at any point of time. You can see here we have smaller and smaller devices which are coming up in the form of watch also, in the form of mapping devices which are mobile. In the field we can do the mapping using real-time kinematic applications. So these are some of the references. One reference has been given here for GPS, one for GLONASS and one for Galileo. For any further details you can contact me at ashutosh@irs.gov.in. Thank you.